Hi, this is chapter 6. This is basically where we will learn about ISA or instruction set architecture. This is where we will be using assembly language. So when we talk about ISA, is a complete collection of instructions that are understood by CPU. Remember, in machine cycle, first we have fetch. We get the instruction from main memory. Then it will be decoded by CU control unit, and it will translate from instruction to command. So this is where the process will actually happen. So from high level language, it need to be turned to assembly language, and from assembly language, it need to be turned into machine language. Then ALU will execute whatever command that is asked and translated by the CU, and the result will be stored in main memory again. So that is basically the machine cycle. So now, in ISA, it is basically serve as interface between software and hardware, because hardware will not understand high level language. So we have C++, we have Java, we have PHP, and those are actually high level language. And now those instructions need to be translated into assembly language. So an instruction is a binary code which specify a basic operation, for example, add, subtract, and or for the computer. And this is typically using assembly code. So in assembly code, we have two sections. One is the operation and another one is operand. Operation is what it will be done by the computer. Add, subtract, divide. So the operation is called the operation code. Whereas operand is the name of the register. So we may have we have 5 types of register. We have PC program counter. We have IR instruction register. We have accumulator, general purpose register, MAR memory address register, and MDR memory data register. So in this case, typically you'll be using accumulator and general purpose register. So how and where it is situated? It is situated in between high level language and machine language. So in high level language, we have compiler that will basically compile into assembly language code. And then we also have assembler to actually translate to machine language. Okay, please delete this arrow. It's nothing to do with continuation. So delete this here. So we also have instruction set in between software and hardware. So in machine code, each instruction has unit bit pattern. For example, okay, we have add, sub, load, and operand can be represented as A or B. So this is what is shown. This is opcode, and these are the operand. So it can be differentiated by the following. First, number of bit per instruction, stack base or register base, number of explicit operation per instruction, operand location, type of operation, and type and size of operand. So, of course, when you want to design an instruction set, you must consider these few characteristics. Of course, the instruction length, whether you want it to be short, long, or you have various variable. Number of operand, this is basically depending on number of register that you have. Then number of addressable register. What does it mean is that addressable register means the data can be overlapped. Okay, in your final, typically data that can be overlapped is X, Y, and Z. The rest, you cannot actually change the value. Then we have memory organization, whether it is byte or word addressable. Typically, we'll be using word addressable. And of course, addressing mode is either direct, indirect, or index. So, before we go further, we need to know about byte ordering or Indianness. Okay, this is another major architectural consideration. So, if we have 2 byte integer, the integer may be stored so that the least significant byte is followed by the most significant byte or vice versa. So we have two types of ordering. We have Little Endian and we have Big Endian. So Little Endian, actually least significant byte is followed by the most significant byte, whereas Big Endian is vice versa. So this is the example. So if you can see here for Big Endian, so we have 1, 2, 3, 4, 5, 6, 7, 8. This is like our normal text. Okay, this is like our normal text. But the Little Endian is actually shown like this. Okay, it's actually reflected compared to Big Endian. So it's like Big Endian is like your Romanized text. Little Endian is like your Jawi. So you write from right to the left. And it's like you writing mathematical numbers. Okay, of course we have small numbers on your right to the left. Okay, so those are actually the difference between Big Endian and Little Endian. So Big Endian is more natural. The sign of number can be determined by looking at the byte address offset 0, and string and integers are stored in the same order. But Little Endian make it easier to place values on non-word boundaries. Conversion from 16-bit integer to 32-bit integer does not require any arithmetic. Now, we are start talking about the assembly language. So, in the next consideration for architectural design concern how CPU will store data, we have three choices. One, we can use stack architecture. 2, we can use accumulator, and 3, we can use general purpose register architecture. So stack architecture is basically 0 address. Accumulator is 1 address. General purpose register is 2 address and 3 address. So of course, it is very much dependent on if you want to have a very simple code, but the length can be a little bit long, or you have very complicated instruction, but the length is very short. So it is very much dependent on what actually you need. So these are some instruction or how we can actually understand. In stack architecture, instruction and operand are implicitly taken from stack. So we will basically take a look at 0 address later. In accumulator architecture, so what is meant here is that one operand of a binary operation is implicitly in the accumulator. What does it mean is that the operation need to be done in accumulator. Then you take whatever result back to the addressable register. Whereas for general purpose register, you can basically make use of the register. So it can be faster, okay, than accumulator architecture, efficient implementation, but the instruction is a little bit more complicated. Okay, most of the system are GPR system. There are 3 types. One, we have memory to memory, then we have memory to register, and we also have load store. So the number of operand and the number of available register has a direct effect of instruction length. So these are actually the instruction format. I will show you explicitly for each address. So 0, 1, 2, 3 address has slightly different instruction format. So let us take a look here. Opcode here, this is 0 address. So notice that we don't have any operand. Then we have opcode and address. This is 1 address. This is, because this is 2 address, this is what we call as 2 address instruction. And this is 3 address instruction. So how to actually read this? So let us start from 3 address first. This is the easiest actually. So what it meant is that R, okay, this is add here. R at R2, R1 at R2. Then the result is stored to R3. Then we have the second line is that R2 multiplied by R3. The result is kept by R1. So this is how should be read. First, we put A in R1. Then we add R1 to RB, and then we store in RB. Okay, and this one is C add to R1, and the result is stored to C. Whereas for one address, again, all the process is done in accumulator. So load A, which means that we take A and put in accumulator. Add B, so A is already in accumulator, then we add B in the accumulator. The result now is stored as C. So A plus B is being sent to C. So now our accumulator is clear. So what is meant by stack? Stack means we will take it one by one. So first we push A, we push B, then we add, which means that A is already in a stack. Then we put B. Then when we have add, it is actually A plus B. Then when we set pop C, we store it into C. So it is like C equal A plus B. So that is how we should read our different addressing. So let us take a look at tree address first. Let's say we have this this equation. So the first thing first, you need to know which should be done first. So looking at this, we must actually solve those inside the bracket. So those inside the bracket is D multiplied by E. Or you can also do A minus B, like this example. So in this example, we do A minus B, we store in X. Then we solve D multiplied by E. Then we store in Z. So we will add, okay, please correct this here. It's supposed to be add CZ. I repeat, please correct this. It's supposed to be add CZ. Because C is add to Z, not the other way around. So please correct this here. Then, of course, we have X here will be divided by Z, and it will be stored in Y. We will discuss further for this. I see you in the next video.